Very good afternoon, everybody. Mattia just set the stage for my talk. So we were a member of the Gamma team, and we consider that a very successful project and a very nice collaboration in the team. So what I'm going to show you today is the optimization workflow for the turbocharger design from the Meshing and CFD Simulation side. Okay, good. So in the first part, I cover the workflow, how we try to stitch all the parts together. Then how do we set up such a CFD simulation in order to make it really robust over a wide range of operating points and parameters. And at the end, I have a few words on the structural mechanics meshing. Good. Okay. The optimization workflow. So the goal here is to have a fully automated, multidisciplinary and multi-point optimization workflow. So that can be quite challenging. So mainly because of the range of the parameters can be really vast. And also the multi-point is a tricky part. So we have to cover a whole range of operating points. So in order to make that a stable and reliable workflow, we need a very robust geometry and grid generation for the whole design space. So Mattia just covered the geometry generation, and the grid generation was our part. We also need a very high mesh quality in order to guarantee reliable simulations and also a reliable convergence behavior. The CFD simulation setup sounds trivial, but again, here you have to take into account the wide range of operating points and a lot of what if this and that happens. And all that has to be coupled in an automated way, covering different softwares. Okay. Also interesting in case that you have to foresee a case where an actually aerodynamically good design can be rejected because of meshing or geometry issues. And in that case, we don't want to lose that promising design. We are going to redirect the optimization into a more stable direction. Good. The optimization workflow. The part you're seeing here has just been covered by Mattia. So cases delivers us geometry for the volute and for the impeller and diffuser. I cover that in more detail later. What we do before we start, what we do inside the optimization, the first thing is to mesh the structural part. So the CSM stands for computational structural mechanics. So we mesh the solid body and calculate and simulate that the structural stresses via Calculix. And then we go into the CFD. The reason for that order is quite simple. The CSM calculation takes a fraction of the time of the CFD calculation. So if a design fails mechanically, we put that into the database in order to maintain the information of a fault design. But we don't run the CFD simulation. The flow result of a design which is structurally not integer is basically worthless. Good. Then we, in case of two successful simulations from the structural side and from the fluid side, we take the CFD and CSM result into the optimization loop. We use in that case an artificial neural network in a genetic algorithm. So we have an adaptive response surface. We get an optimized design. We feed that into the database. We modify the parameter back into cases, and the whole loop starts all over again. Okay. The proof is in the pudding. How to couple different softwares. So we have on the geometry generation side from cases delivers us an impeller with splitter blades, plus the diffuser and plus a volute. So this is on the fluid side. And additionally, we get an impeller section, the impeller solid body for the structural side. We couple that via parasolid files and geom turbo files. Turbo is a native NUMECA input file for the meshing. And we also need additional curves, in particular for the volute. And meshing template, this is what we're going to provide in order to turn the geometry into a mesh. Then we mesh the different parts, the CFD part, the structural part, and the volute. All has been done by different philosophies, and we stitch all that together to a workable mesh. Good. Let's cover that section about CFD meshing and simulation. Before we set up the optimization, what we do first is manually meshing the first parameterized design. Manual meshing is not an option inside optimization, that's obvious. But for the first shot, we optimize the mesh manually, have a close look, and quite important, we take a grid convergence study in order to find a good compromise between a good, solid CFD simulation and an acceptable mesh size. So since we are running hundreds of design, it's basic, every mesh point counts, I would say. So we try to minimize the overall mesh size and still maintaining a good accuracy. Part 3 is just a simple sentence, automation of volute meshing, but it was really, I would say, a major part of that project to make a volute, to mesh a volute automatically, robust over the whole design space in a structured way. I come to that later. And at the end, we run robustness tests for the geometry and the mesh generation. A robustness test means we're just generating hundreds of meshes over the whole range of possible parameters, possible parameter combinations, and we check whether the mesh is still a good mesh after even very strange parameter inputs. So that's important to guarantee a high rate of success, however the geometry looks like. Technically, we mesh the impeller and the diffuser. We have a multi-row mesh. We use one passage for the impeller. We use a 360-degree mesh for the diffuser, and the volute is also meshed completely, obviously, and then we stitch that together. Now have a look in, let's look into that in more detail. Cases delivers us the impeller plus a vane diffuser in a parametric geometry generation. We export that as a Turbo. This is a native NUMECA autogrid input file. It's a simple ASCII file, very clear. We're going into autogrid 5, which is NUMECA's block structured meshing tool for turbo machinery components. And we run the mesh generation in batch mode. We use so-called templates. A template is a model describing the mesh parameters in the sense that we specify how many points we have on the pressure side, how many points we have on the suction side, in the tip gap, blade to blade, and so on. So working via templates guarantees us that all the meshes are of similar quality and of similar quantity. So this is one thing you can do very nicely with structured meshes. Finally, we export that mesh. You see here, this is the compressor impeller, the impeller plus a diffuser. So it's a multi-stage mesh. We incorporate the tip gap. We have blunt trailing edges in case of the impeller. And we also take the real geometry of the bulb, meshing down to radius 0 into account, and also the blade fillets here around this splitter blades and main blades. We did not do that here, but seal leakage and cavity flows can also be taken into account. Okay, now let's come to the volute. Very early on in the project, we decided to use a block structured hexahedral mesh for the volute. So many people would say this is a hell of a work, and they are right. It was quite some work, but we deliberately decided for going for structured mesh in order to guarantee a high mesh quality and also to have a very fast solver speed. So typically, if running a structured solver can be about 3 times faster than running an unstructured solver, and we wanted to take that into, we wanted to take that advantage here in the optimization. So the decision was for block structured hexahedral mesh. The challenge is the tongue region. So the rest of the volute is basically just a bended tube, so that is fairly easy to do. But where the tube is matching the other tube, that can be quite tricky. This is so-called tongue, and here you have really to think hard about how topology to use. Okay, here's a close-up look, and you can already see the block structure is quite interesting. And it was, as I said, quite a challenge to make such a block structure robust over a whole range of geometry variations. Good. How does a block structure look like in detail? We used 2 rings, an inner ring, the red one, and an outer ring which wraps around the inner ring and closes into itself. And then we have a transition block here. And this is the main topology we're using. There are much more details in the real world, but in the frame of that talk, that should be enough here. This is a close-up of the mesh. It's not the mesh we used, so the real mesh is quite a bit finer, but it should give you a flavor about the block structure. Important was, as you see here, quite a number of curves. So these are additional curves we use for the stabilization of the meshing process. And here a very close interaction with cases came into play. So cases delivered us these curves, also in a very parametric, robust way, which we have to use for that purpose inside the optimization. There was a lot of fine-tuning involved, of course, and these curves has been exported in parasolid format into our mesh. Okay, so this is how a volute does look like in cases, and we took these curves, these supporting curves for our meshing process, incorporated in our meshing tool IGG and started meshing. Good. So the entire meshing process here was script-based. Again, it's a Python script which reads in the cases curves and surfaces and starts our meshing process. Export came from Parasolid into IGG, which is our manual mesh generator, which we did not run in a manual way, but in a script controlled way here. And then the blocking started, as you can see here. And the next point was the optimization of the grid point distribution. And finally, we mapped the final mesh here onto the final geometry. You see here, there's this discrepancy between the geometry and the mesh. We use the conformal mapping to put the mesh exactly on the surface. So out comes a meshed volute. And finally, we put all that together. So the volute, impeller, and diffuser is a close-up. And you see a beautifully structured mesh of a complete turbocharger impeller. Good. So far for the meshing. How was the CFD set up? So here's the mesh. And we went into, put the mesh into Fine Turbo, which is our turbo machinery specific solver. It's probably the fastest turbo solver on the market. It's a structured solver. It has a very high quality and reliability. And I think the simulation time we have here is really competitive compared to unstructured CFD solvers. Again, full batching and scripting capability is important inside an optimization process. So here's a numerical setup. As I said, we have the full volute naturally, we have the full diffuser, and we used one passage of the impeller. Before we started, we made different studies on turbulence models, inlet-outlet boundary conditions, interfaces. So a lot of variables we had to play with before we went into the big optimization. Again, robustness tests were here a topic as well. We used for steady-state simulation, we used total pressure in the inlet here. We used in the outlet around the design point and stall point, we use mass flow, and the choke point, we use static pressure. So this is the beautiful mesh boiled down to the numerical setup. You see here the solid surfaces. The red part is a rotor-stator interface. This is the diffuser blade. And here we have what we call a full non-matching boundary condition, where we connect the diffuser to the volute. Good. If you run a multi-point optimization, you naturally have to run multi-operating points. And there are several ways to do it. So we have the design point, choke point, and the stall point. You can run all 3 points simultaneously on a number of processes, which in total speeds up your computational time. On the other hand, starting an operating point very close to the stall can be a bit tricky. So we decided in most of the cases, we decided to take the design point as an initial solution. And from then we went to the stall point and the choke point. In case a steady state simulation is not enough for the optimization, we considered only steady state. But for a detailed look into the flow, we were interested in the unsteady solution. We used the nonlinear harmonic method. The nonlinear harmonic method is a quasi-unsteady method. I try to explain that in a nutshell soon. It gives you mostly an improved time mean flow solution. Even if you don't look into the unsteady results, your time mean flow is improved quite a lot. The continuity across the rotor-stator interface improves by using the nonlinear harmonic method. And we have no restrictions on the number of blades and blade rows. Computationally, only 1 blade passage is taken into account, but that can be periodically multiplied. So how does the nonlinear harmonic method works? Traditionally, if you use a classical time-stepping approach, you have the full model. So that's what we call a 360-degree model. So you have to mesh the full impeller and the full diffuser, and then you step the impeller in tiny steps until you have completed a couple of revolutions. So this gives you big meshes and many, many time steps. So what people try to, when people try to take a shortcut, they find common integers between the impeller pitch and the diffuser pitch, and multiplying the pitches a bit and stretching them. So that works basically the same way as a full model, but with a reduced mesh. But here, your frequencies are not longer the same because you play with the blade pitches. So we're using a nonlinear harmonic method, taking only 1 blade passage into account for the impeller and 1 for the diffuser. We use here a Fourier decomposition. We're considering transforming the Navier-Stokes equations into the frequency space. Time-wise, the speed up is very considerable. Today, a run simulation takes a couple of hours, depending on your mesh size and number of processors. The nonlinear harmonic method is about, let's say, typically takes 10 times more time than a Reynolds, the classical run simulation, but we are still in the range of hours, while a full unsteady simulation, we are close to days and even weeks. A validation of the results. So this is a snapshot of a full unsteady simulation of our impeller. You see here that's an entropy plot, entropy leaving the impeller, entering the diffuser. And here we use a nonlinear harmonic with 3 and 12 harmonics. You can see the differences between a classical unsteady simulation and nonlinear harmonic simulation are negligible, but there's a factor of 50 in the computational time. Good. The final part here is the solid body mesh. How did we mesh the structural part? Again, cases delivered as the geometry, a fully parametric periodic segment of that impeller plus splitter blades. You see that here. So slice through the cake, and the CSN solver Calculix we use accepts only tetrahedral elements. So our measure delivered a hex dominant mesh. So we have to take something, we have to do something for that. There were quite a number of requirements. So we had to use more than one cell per blade thickness for accuracy reasons. The leading edge and the fillet capturing should be as exact as possible. And we need to have a matching periodic connection on both sides. We used the surface to volume approach in hex plus hybrid, which is our unstructured measure. We got the geometry segment out of Parasolid, and we used what we call a configuration file with a number of keywords, also specifying the main parameters of the mesh. Good. So from cases, we get the parametric model. Being exported as Parasolid. Hex plus hybrid first creates a hex dominant mesh with a periodic matching connections. You see here that's mainly a hex mesh. And in the next part, we are splitting that hex mesh into a tet mesh. And then we export that into Calculix. The features, as I mentioned before, so you see here we have a fairly accurate capturing of the fillets. We have between 2 and 3 elements over the blade thickness, and also a quite good approximation of representation of the leading edge here. And the mesh was periodic matching. So finally, we got what we wanted, impeller segment consisting only of TETs with all the quality requirements we imposed on the structural mesh. So that was the entire optimization workflow, starting with the geometry generation to the CFD meshing and simulation, the structural meshing and all that put together into the optimizer, and finally leading to a better design. So that was my talk. Thanks a lot, and I'm looking forward to the Q&A.